do, okay? Yes, so welcome to this first session today, and we have a session on random processes, non-Archimedean operators, and heat kernels, and this is the first of two sessions. We have one tomorrow too. And welcome to Professor Kaneko, who will talk on chip firing on ultrametric space and Riemann-Roch theorem. Please, go ahead.
Thank you very much.
Me? Yeah, okay. Okay. You heard
can
me.
I hear?
Okay.
Can you hear me?
Yes, yes, I can.
Yes, okay. Before my talk, I would like to send my thanks to the organizers who came up with a nice idea, many of interesting talk, spill over the globe, and this epoch-making conference could be very interesting, and I would like to send thanks to the member who helps this conference, especially technical setting could be very difficult rather than usual conference. So I would like to send thanks to them as well. And I apologize, my title is delayed and replaced probably yesterday, and still the abstract is missing. So I would like to send my abstract as a chat. I hope this way of providing chat abstract is successful.
Okay.
Is it okay?
Yeah.
Okay, thank you. Sorry for inconvenience of delay in sending title, and that abstract is missing just before my talk.
Oh, that's fine.
Okay, I would like to talk about chip firing on ultrametric space and Riemann-Roch theorem. First, we give a sort of assumption. We take a finite graph G consists of V and E. V is a set of the vertices and E is a set of edges. On the set of V, we take a finite family of functions. Each of which is non-constant and z valued, and the space B is assumed to admit random measure mu, and we have assumed that finite subset of 0 infinity interval, including 0, and this is viewed as a set of radius. Okay. On the family of the function G, we assume the following. First thing says the average is 0, and each k admit a vertex and radius R in the set of radius except 0, such that support Fk is included ball centered at X with radius R, and either Fk is non-negative on the ball centered at X with radius S and non-positive on the annulus-like domain O S in 0 R interval, and that is in the set of radius, or so it's signal inverted Fk. In the next, we assume that all linear combination of Fk with Q rational coefficient contains all functions in the potential space Lk that consists of function on V, and average is 0, and value is taken in Z. why this, I would like to explain why this assumption is natural in p-Adic model. I would like to find the reason in p-Adic model. Before that, I would like to give a distance between V and W of distinct points in V. D of VW is given as a maximal element in the set of radius such that R is associated with some fx satisfying condition 2. 2 is given here, right? The domain and the small ball inside the annulus-like domain is separated in terms of the value of the function. Okay, and the condition 2 is satisfied, and the signum of fkw and fkz has a different signum. And then we assume that D is a non-Archean median metric on V, as in ordinary scheme. Any function f on V can call the unit of chip firing. If f is coincided with fk or signum inverted fk in the family of function. Okay, why the name of chip firing? Somebody asked why name of chip firing is natural. I would like to show you the reason. Oops. In p-Adic model, we take a prime number z, p, and zp admit a normalized Hall measure mu, and take a family of balls with radius p to the power minus m. Here, we regard ball as a singleton. For any pair B and B prime in V, distance between those two balls is given as a minimum of p to the power n minus pm to n to the power n minus m, such that B over Pn includes B prime and B prime over Pn include B. Then for any pair B and B prime viewed as edge and edge weight CB B prime is given in the article written by Kigami and mine. That is a key factor of contraction of Markov process on V, where B over Pn is given as a set Z over Pn, where Z is in B. Okay, now show the function given here, written as F1, is inward chip firing. When M is 1, C is represented as a union of disjoint balls with radius P. We can take a following function as an example of a family of function called G. The first function written here is also viewed as inward chip firing. This is because those p-1 vertex lose a unit weight. Minus sign means losing unit weight, and the sum of lost weight is p-1. The p-1 is sent in a lump in the center of this graph. Okay. In the next, this is an image picture of the inward chip firing. And we still need p-2 functions, and these are nothing to do with inward chip firing. This is because here vertices that lose unit weight, and the sum of lost unit weight is sent another ball, another vertex, which is still outside the central vertex. So these are nothing to do with inward chip filing. Okay. We have just defined the metric, and the metric D is exactly same as the p-Adic metric, and that is obtained from the set of radius consisting of 0 and 1. In m equal 2, in the case m equal 2, Z is decomposed into p squared balls, where those are obtained as the image of these functions, and in addition, F1 from F1 to Fp minus 1, that is shown previously when in the case m is equal to 1, but we still need other functions, and in the bottom of the screen, we find a family of function with frequently changing in its value. In the contrast, from F1 to Fp minus 1, we see less frequent changes in the values. So we arrive at the context that metric D is defined, that is also exactly the same as the p-Adic metric, and that is obtained from the definition of R consisting of 0, 1 over p, 1. Okay. We can classify the function in G in the previous example with m equal to 2, according to the diameter of support of function with respect to non-Archimedean metric D, G 1 over p is given as a family of function with diameter of the support is 1 over p, and G1 is given as the family of function whose diameter of support is 1. So, oops, it's not working. So, sorry. Wait a moment. Just a moment, please. Okay. Here we need abstraction, our assumption which is viewed as abstraction of the family of function in example one. There exists, the assumption says here that there exists an orthonormal family of function G of Q-valued function with respect to a fixed positive rational valued measure mu, and each function in G is orthogonal to constant functions, and that any G in calligraphy G, we say that Laplacian G is Q-valued, and the support of G and its Laplacian is the same. Sorry. Just a moment, please. Okay. here we need the definition of Laplacian, and the Laplacian of f is given as sum where Cx and difference of the value of function f between the point x and y is involved. In the recent scheme of Markov process on non-Archimedean space, orthogonal system, as in example, plays important role. This is because in the scheme, the family is dealt as a family of eigenfunction, and especially Laplacian of f is equal sigma inverted lambda f. So Laplacian of f is viewed as a chip firing as well. We introduce the Ix that is viewed as minimal current flow when voltage level is given as a function f, where f is g value and x is the point x is grounded, and Laplacian of f is not zero at that point. Okay, and we regard D written as the sum of Lx or Ix times indicator function of singleton x on V with L given as a function from f to z as the divisor. And degree of the divisor is given as a sigma of Lx Ix. That this enjoys the following, namely, degree of Laplacian f is 0, and degree of the divisor is invariant under the sum of Laplacian of some function f. So we call each function written as Laplacian f a chip firing. Now we define the equivalence between two divisors, D and D prime. Their divisor on V are called equivalent if D and D prime plus Laplacian f for some z-valued function f. This equivalence is denoted as wave sign. We denote the set of consisting of total orders on V by calligraphy O, or more specifically by OV. I would like to say why this total order is important. These are the following. Similar to the observation to Baker and Noreen, who established the Riemann-Roch theorem on discrete space. Similar to their scheme, the minimization of the positive degree given here of D plus Laplacian f minus nu O subject to f is B from B to Z, and O is in the calligraphy O, where nu O is divisor given by this one, is required. In fact, the dimension, that is a very crucially important notion in Riemann-Roch context, usually denoted by RD, that is given as a minimization of value given here, where IGC is given as a minimum of absolute value of sum of Lx Ix, where L is from V to Z. Now we consider a little jump is happening, I think. Oh, that is correct. Now we take a arbitrary fixed point V0 in V, and RJG is given as a maximum in the set of radius such that support of F is included in volume centered at V and radius R for any F in G, then we need JG dimensional vector and JG plus 1 dimensional vector. First one, it has a component, first one of which is given as a sum, where the sum is taken over the circle with largest radius, and only negative coefficient is summed. And eventually, and radius is shrinking, and eventually, finally, in the final term, final component, the sum over the circle, I mean, with smallest radius is taken. In the next one, B to D, we have reverse order in the radius. I mean, first, this one is exactly singleton of V. I mean, S0 equal singleton consists of V0, and radius get larger and larger, and sum is taken over circle with maximal radius. Okay. To obtain maximum of B1 D prime, where D is equivalent to D, in the sense of lexicographical order. Lexicographical order means first important thing is attain maximum of the first component. The second important thing is taking maximal value in the second component, and on. And we can take this sort of maximal element, and we use F gives the linear combination of the function G, which is contain positive rational coefficient of inner chip firing or outer chip firing. This is I show this figure because this is a circle-wise operation. This component has large. The first component of V1 has involves most largest circle. The final one is the smallest circle. So this sort of inner chip firing and outer chip firing is such sort of adjustment for taking maximal is very important. Now we take D prime consists of divisor that attains minimum of maximum of B1, and in the second we take subfamily D prime, D double prime of D prime, each element of which attains maximum in the second vector in the sense of lexicographical order as well. After taking D double prime, the element is, D prime is called V0 reduced divisor. If once we get this one, we can determine total order. At last, we come across the story on total order. In fact, we can determine a total order as follows. The smallest element with respect to the total order is given as V0 in the next second smallest order is given as the element satisfying design inequality. The element is surely found because of the V0 reducibility. We can continue this procedure and the next smallest element is found on V, the set of vertices. After assigning total order on V and the subsequent minimization of positive degree written here, and the dimension of RD is given as here with the minimized value of the right-hand side. I mean, the first term of the right-hand side. And canonical divisor is given as capital KG, which is given as this one, very similarly to Baker-Noriman's scheme. We can derive the following identity could be called Riemann-Roch theorem, where in the second term in the right-hand side, EGC, that is given as a degree of the canonical divisor, and that is exactly of the sum of Ix and edge weight. Edge weight must be subtracted from the first sum. That is viewed as Euler characteristics. I mean, namely 1 minus G with genus of G. Okay. Now we consider the splitting and enlargement of the graph. First, we start with splitting. If you have a graph G, that is a complete graph equipped with ultrametric, and we divide the origin graph G into G0, G1, Gm, where V0 is a difference element. Difference element means given as V0 between here if the single graph is given, in the case single graph is given, and I mean V0 here is a sort of representative element from the graph G0, and it is a reference point of the graph G0. And naturally, we take V1 as a representative vertex from the graph G1 that can be taken as a reference point. And we can this process continue. We can continue this process, and we obtain graph G0 graph Gm. Corresponding to the splitting of G into G1 to Gm, the graph over line G is given as a set of vertices, each of which has a grouped set of vertices from the first graph, and V1 is viewed as a singleton here, and it is given as a second vertex set in the second graph. And we have from a set of vertices from V0 to Vm. Now we take a set of edges, each of which is given as a pair V1, Vj, and define conductance between V1, Vi, Vj could be called bundled edge the component of which is given as conductance bridging B1 and Bj. Okay, if you simply write Ix, it is not clear which graph is in background. I mean, which graph which is without specifying ambient set of vertices, we cannot say what is the minimum current flow. So at X, we more specifically we denote Ix if it is required. The next assumption says that these minimum current flow from the individual graph is I don't know what would say it in English. V0 from Vm is completely separated, and we would like to see the minimum current flow at X. And these are all integer multiple of minimal current flow. Laplacian is where Laplacian is and described in terms of conductance, and the function f viewed as a voltage level given as a function defined on V bar to Z, where Vj is grounded and Laplacian is not zero at Vj. Okay. The second assumption is abstraction of the example in the first section. We can recall that in this way. We observed this system of family of function, and we need an abstraction of this example. That is assumption 2. It says here that for any radius and then by taking S in the interval R to infinity and in the set of radius and SG given as this satisfying this inclusion, and it is positive and it is negative, where the separation of balls happens according to the signum of G, and those two balls has no intersection. And here assume that consists of linearly independent M functions, including a unique function f, such that f is positive near the center and that is negative on annulus-like domain. And so is signum inverted Laplacian of f. Okay. Minus Laplacian f is gives an inward chip firing with respect to V0, and original function, I mean Laplacian f itself gives outward chip firing with respect to V0. In the sequel, we need a family of function in G that contains neither inward chip firing nor outward chip firing in its linear combination is denoted by HS. For any divisor on V, we can give an algorithm procedure to obtain V0 reduced divisor on the for graph G that which is equivalent to D by taking one of V0 from V0 to V0 VM as V0, and for that purpose, we divide into D into M plus 1 divisors, like this one. The restriction to E0 to Vm is performed, and they are divisors given on these subgraphs. For the divisor D is a divisor D is said to be effective if all coefficient is non-negative. There are many cases if you classify this situation according to which divisor is effective, which one is not effective. For example, to a little bit complicated situation, more clear, we can draw a picture where red ball means effective divisor as a graph which has effective divisor. Blue one is graph that has non-effective divisor, and we can manage. Sometimes we need perform inward chip filing, and blue one, so that blue one turns to red, like this one. So this process is very crucial to find the, difference point in the whole graph. The time is strict, and we skip some details. The story follows after the choice of the selection of difference point. Anyway, we can take a situation that we can observe a situation that if we are given a central graph G0, and by adding graphs in the bottom to the central graph, and we obtain as the union of G0 to these with this one, and these ones, we obtain first step of enlargement. You can repeat this in enlargement procedure, and we observe the situation that the size of graph is increasing, and we assume that the maximum volume of grouped vertices is dominated by constant time minimum of conductance linking central graph to satellite-like graph. That satellite-like graph means that it's not that does not come to the center, and the number of satellite-like graph is totally controlled. That has an upper bound, uniform upper bound. And we need a little bit of technical comment on the definition of divisor for graph. For graph means set of vertices is given as the union of infinite vertices, and associated with set of edges that is also have infinite cardinality. And degree plus positive degree of D is given as this, the way of after observing the consistency of d dash of d double prime, each of which is given as gd prime, gn prime, and gn double prime. Okay. And the most important thing here is for any, I skip one explanation here. We denote family of functions presented as a rational multiple of chip inward and out or outward chip firings in the function settled on the J label. J labels means we suppose that we are just come across the situation as the growth from Gj to Gj plus 1 is seen, and according to level, a sort of distant detecting function in the first example is given according to the size of the support. That the size is measured in terms of diameter of the support of F. Okay. We assume that this GRJ fulfills the previous fulfills all assumptions previously assumed on GJ. So, as I told you a little bit before, the family of function represent as a rational multiple of inward or outward chip firing is this denoted by this notation. For the minimizing procedure of the positive degree of the divisor by adding Laplacian of f, it is important to see that in this step means growth from J level to J1 level. Only two things can happen. One is the positive degree out inside of the ball, on inside of the graph is erased by a negative degree of the satellite-like domain, satellite-like graph, or positive degree on graph outside the central graph is erased by the negative degree of central graph. I mean, in divisor sense. So the powerfulness of f is completely limited. So we have this estimate for the function of in the process of minimizing procedure, and we have this one. We can proceed this one, and minimization is successfully achieved by the previous lemma because we have that is very optimistic because we have the powerfulness of the function f is totally controlled. So we have this estimate as well, where the minimization of positive degree minus I of G and constant function is achieved for some function. It is called minimizer. For the minimizer, we have the following estimate.
You have 5 more minutes.
5 more minutes, thank you. Now we assume that total sum of conductance is finite. every function on Gn admit harmonic extension denoted by G, and Laplacian is of f and G is exactly same in a graph, and outside of in a graph, the Laplacian of G vanishes, and this powerfulness of f is controlled, and G is dominated by the powerfulness of f. So we have this sort of lemma where Laplacian of f outside the inner graph is totally controlled and converges to zero as limit is taken as into infinity. So a little bit complicated thing of total order, and it is well organized by taking a subsequence, and this sort of consistency between total order in the sense this restriction of total order of given on the larger graph is exactly same as the total order in the small graph, and this sort of inequality is valid, and as k and l is go infinity at the same time, this is very small. That is the point. So if you have a modified counterpart of maximal one-step exit probability from the graph in the inside that is given as a low end, the maximal and the sum is taken where the conductors bridging in a graph and outside of inner graph is given, and this should be given, should be divided and the total volume of the inner graph. If this convergence is correct, this one is, it turned out this one is converges, and as k goes to infinity, and while this process we need a subsequence so that total order is controlled very well. Okay, RNL is given as this one, and if you take harmonic extension of inner graph for the minimizer, this one cannot be always minimizer, and this one is dominated by this one, and this we can see this part, the bridging effect between inside of the in a graph and outside of it. The we already seen that bridge effect is very small, at least controllable, and these things is very small, and we can discuss like this, and dimension of divisor is it's defined through this limit. In fact, RD is defined as a infimum of choice of total order, and where after that, before that, where we need L tends to the procedure of L to L goes to infinity, and we already justified this one in the previous page at the bottom here. And next, Kg is defined as a limit of chemical divisor on the n-level graph, and this one is given as a parallel procedure in defining RD, and Euler characteristics for graph is given as the limit of the ones, each of which is given subgraph sequence of some graph. And finally, under this assumption, we can get Riemann-Roch theorem on infinite graph that has non-Archimedean property. That's it. Thank you for your attention.
Thank you very much. Any questions?